It's a pleasure to talk to you today about modeling plasma physics and the Zpinch fusion concept. On this slide, do I have a pointer here? Nope, don't use a pointer. It's okay. There must be, but RPE is one of our sponsors. They're a Department of Energy group that supports energy startups. University of Washington is also a close partner of ours. But I also want to mention that Chevron has made an early investment in Zap Energy, and their investment is the first of its kind of an oil and gas company in a fusion company, and we're proud to recognize that. And we have several other great VC supporters, including Addition, Lowercase Carbon, EIP. And before I launch into the talk, I'll give you a brief overview of our company and what we're all about. We are a company dedicated to developing fusion energy technology that's commercially viable. And we are focused on a small modular fusion reactor concept that magnetically confines plasma without using magnets. And this is an advantage because neutrons resulting from, oh, thank you. Okay. Neutrons resulting from nuclear fusion can damage magnets, which are often made of a sensitive superconducting material in conventional fusion ideas like the tokamak, for example. Our small reactors are also intended to be about a factor of 100 cheaper than a tokamak fusion reactor core. So we have a growing team, 45 people and growing, assembled from industry, academia, and national labs. And we are aiming at some big goals. Early next year, we hope to have reached energy break-even, where the fusion power output from the device is as much as the power in. And in 2025, we're aiming to have a demonstration fusion reactor, and by the end of the decade, a first-of-a-kind fusion power plant. And we are in the midst of a Series C raise of funding to allow us to push ahead with these aggressive goals. And so, if you know anyone who might be interested, please contact our investment folks. You can also just write me a check after the talk. I'll take that. So here's our theory and modeling team. The first four on the list there have done the work that I'll present in this talk. There's Yuri, myself, Peter Stoltz, and Iman Dada. And I want to mention we've added a couple of wonderful new people who will be starting, well, they started yesterday. So I want to mention a family connection to oil and gas that I have. I was born in Shreveport and grew up in East Texas. And my grandfather, Bill Meier, worked in the East Texas oil field in the 1930s. So this conference has kind of a special meaning to me from that point of view. Here are a few pictures from his collection. There's a picture of him in front of a floating pole derrick in 1935. There were always lots of great stories from the oil fields, a lot of humor. Everybody had a nickname. Here's a group of people up here on one of the jobs, and one of these guys is my great uncle. Here's a guy named Tiny. And here's another dramatic scene that was in the scrapbook of an oil well fire in Kilgore. And I remember a conversation with my grandfather when I was young, still 10 years old or even younger. I knew I wanted to be an engineer, and he advised me that oil and gas is a boom and bust industry, and you ought to consider diversifying into some other kind of energy. And so here I am working on fusion energy today. So the outline is that I'll give you a high-level introduction to fusion energy and the stabilized Zpinch. Then I'll tell you about some of the physical models and computational tools that we're using. Then I'll highlight some simulation results and doing two-fluid modeling of instabilities and Zpinches, PIC modeling of fusion alpha particles, and what we call domain hybridized modeling of plasma sheaths. And then I want to touch on our whole device modeling plans, which is really where we engage all the HPC resources we can get our hands on. Okay, so fusion, what is it? Well, it's the ultimate energy source, a star in a bottle. It's clean, it's safe, it's on demand. I want to show just two figures that give the high-level physics idea of what's happening in a fusion reaction. We can merge together, fuse together a deuterium and a tritium atom, and out come an energetic neutron and an energetic helium nucleus called an alpha that we can harness to actually produce electricity. And this curve here is related to the what's called the nuclear binding energy. And you can see that if you start on the left with these light elements and you fuse them together, you move down toward iron and release energy in the process. And it's interesting to note that a star actually burns all of its matter in its core, or it can, down to iron as it extracts all the energy from the matter. You can also move from the right with something starting from uranium, for example, and split the atom and also move toward iron and release energy. Okay, so there are many approaches to fusion energy. There's gravitational confinement. The sun works well. There's inertial confinement, where here's a picture from NIF at Lawrence Livermore, where lasers are focused on a very small target, that gold cylinder there, and result in nuclear fusion. And then there's magnetic confinement, which is the focus of this talk, and we think is the most promising way to get to commercially viable fusion power plants. Back in the early days, at 1945 to 60, people were already working on nuclear fusion and explored a lot of different concepts, including the Zpinch, actually, back in those days. In the 1950s, the Soviets developed the tokamak. And this approach actually took off worldwide starting in 1969 when a team from the UK went into the Soviet Union and measured the temperature in a tokamak and found that indeed it was as hot as they said it was, and this was an attractive thing. These other concepts had problems at that time. And so that's kind of brought us where we are today with the ITER project, which is shown in this picture at the lower right. It's a very large, called a tokamak. It's essentially a donut-shaped device that holds the plasma inside the donut. There's a person at the bottom for scale. This is an enormous project. It uses superconducting magnets, and it has a long timeline to develop a functional power plant. And so this motivates looking at other ways to do it. And so we have been working on the Zpinch, which offers an attractive path to fusion energy. Here's a schematic of one of our devices. It's compact, 1.5 meters long. And when we form a Zpinch here in this, what we call assembly region, with current flowing along the z-axis, this is a cutaway of a cylindrical device, so the z direction is left to right here. Currents along this z-axis, and a magnetic field encircles that current. And then there's a force related to the current multiplied by the magnetic field that actually pinches the plasma together, as indicated by those white arrows. Now, assuming adiabatic compression, as we increase the current, as shown in this plot over here, we get to fusion conditions. And an important quantity to think about is the ratio of the fusion output power to the input power. And we call this Q. And if we look at the line for Q, this black line, which corresponds to this scale for the DT fusion Q, or deuterium-tritium fusion Q, we see that above about 600 kiloamps, we exceed Q equals 1. And then as we move to a megaamp or more, we get to Q greater than 20. And this is now a plasma that's suitable for a fusion reactor. Our key innovation is sheared flow in the Zpinch. The Zpinch is classically unstable to modes called the sausage and kink modes, which are depicted here. And these are the modes that they experienced back in the 50s when they experimented, when they first looked at Zpinches and found that they were not stable and didn't seem suitable for fusion. It turns out that you can stabilize those modes by adding an axial magnetic field, by having an external magnet, or by having a very close-fitting conducting wall, but those aren't compatible with confining a fusion plasma. Instead, we found that we can stabilize the plasma with radially sheared axial flow, as shown in these figures at the bottom. The white arrows indicate the flow, and so you see that there's no flow in the middle, for example, and increasing axial flow as we move out radially. And now as an instability starts to develop, it gets sheared apart, and it's prevented from damaging the confinement properties of this scheme. The FUSE experiment is an experiment we're still running at Zap, and it has demonstrated sustained neutron production. Here's a paper that shows results from that experiment, and for 8 microseconds, we produce fusion neutrons measured by scintillation detectors, and this middle panel shows the accumulated neutron yield. The bottom panel shows the current and the red trace, and we have this plateau of current in the Zpinch for approximately 8 microseconds corresponding to the neutrons. And this blue line shows the stability of the Zpinch, which is below a threshold, and so in a quiescent state for an extended period of time. I'll also mention we've pushed this device to over 500 kiloamps of current now, and results from this device continue to guide our next steps and reactor development. So now for the physical models and computational tools. I've lost some of the equations anyway, and I don't want to dwell on them too much because I know lunchtime is coming. But I wanted to give you an idea about these models because this is one of the impossible problems that we can try to tackle with HPC resources in the future. A kinetic model of a plasma is maybe the most fundamental model that we would attempt to solve, and it involves evolving a distribution function f for a species alpha and combining that with Maxwell's equations, which are shown over here. You can see that the electric and magnetic fields enter the Boltzmann equation, and the Boltzmann equation enters through the current density and the charge density, and the way those evolve in time according to that equation. This is a 7-dimensional distribution function, 3 dimensions in space, 3 in velocity, and 1 in time. This physical and velocity space together, we call it a phase space. And to model the distribution function for multiple species in a global simulation of a plasma fusion device is not possible right now. But who knows? We can maybe try to make it possible. Here's an example of a distribution function. This just says f of the x velocity, and this is the x velocity normalized by the thermal velocity. And in this distribution, the highest probability of finding a particle is here at 0 velocity. And as we move to a couple of thermal velocities in either direction, the probability becomes much lower. Now, I've added a subpopulation of particles that are moving quickly in the positive direction. And overall, this is a non-Maxwellian distribution. And in plasmas, it's often quite important to be able to actually capture these non-Maxwellian effects or kinetic effects. One method of doing this is called PIC. This actually was shown in Andrew's talk as one of the codes that is used in exascale computing. And the way that works is you basically have superparticles that represent 10 to the 8 or more actual particles, and you have velocity space bins in which these particles live, and statistically you can represent a distribution function with whatever shape it has. A problem comes in with noise, and it can be reduced like the square root of the number of particles you have, but this is a challenge for PIC methods to deal with that noise. I'm only showing one velocity space dimension here. Of course, we have up to 3 dimensions in physical space and 3 dimensions in velocity space that we may need to capture to understand, say, the physics in the Zpinch core. Here's a picture from the Lawrence Berkeley WarpX code, which shows a laser-driven acceleration of plasma. These little white particles here are the electrons that are modeled by the PIC algorithm. Okay, so another way to do this is to use continuum kinetic modeling. And this is indicated by this green piecewise linear representation here, which is just a simple way of representing it. Of course, we can use high-order polynomials and maybe gain efficiency. But in general, we have an improved computational efficiency compared to PIC, so this is appealing. At Zap, we use the WarpXM framework for continuum kinetic modeling. Here's an example of continuum kinetic modeling. This isn't supposed to be offset like this, but this is the physical space left and right and the velocity space up and down, and there's one fluid that's moving quickly to the right and one fluid moving quickly to the left. We call this the two-stream instability. And these streams tumble over one another and form a phase space vortex, which is kind of a cool phenomenon. Now we can reduce these kinetic models to something more tractable by the usual method of deriving fluid models, taking moments of the kinetic equation or the Boltzmann equation. And these multi-fluid models end up with a moment over just the velocity space, integrating out that velocity space to come up with a density evolution equation or continuity equation. If we multiply by momentum and then do that same integration, we get a momentum equation. Likewise, multiply by kinetic energy of the particles and integrate over velocity space, we get an energy equation. And the validity of these does require that, that the distribution function is Maxwellian, and we miss these kinetic effects, but they can still be very powerful tools. If we model electron and ion fluids, we have the two-fluid model for a plasma, and we still couple, by the way, in that model to Maxwell's equations. We've, over the years, developed several different multi-fluid models in WarpXM, including that two-fluid model, but also models that have neutral fluids like atoms and molecules, which it can be important to track as well. Here's an example of a two-fluid simulation of an electron drift instability that gives this fishbone-type instability pattern. And finally, we have a magnetohydrodynamic or single-fluid model, which is kind of a simple but still useful plasma model. We call it MHD. It's derived by assuming that ion and electron densities are the same, so there's no charge density. We assume the electron mass is negligible and let the permittivity of free space go to 0. So this simplifies Maxwell's equations, and we just have a simple curl of B is equal to J equation relating magnetic field and current. And now we have equations just for the whole plasma, continuity equation, a momentum equation, an energy equation, and now we have this generalized Ohm's law where the generalization comes from taking into account the electric field you get related to plasma moving across magnetic field lines. So this is a simple 8-variable system once you take into account 3 momentum components, and it's possible to take relatively large explicit time steps. We kind of prefer explicit time steps. It's actually easier to parallelize that in general than an implicit system. And so this is an attractive system as well. Here's a Mach 2 simulation result of the fuse device, which I'll talk a little more about at the end. Okay, and then just a high-level look at WarpXM, this code that's kind of our principal code. It's a flexible framework for high-fidelity plasma modeling, and we use high-order finite elements in multidimensional unstructured domains. We have high-performance modular solvers, numerical fluxes, time integrators. It's MPI parallelized, and we're starting to think about GPU acceleration. We have a variety of different models that I just talked about, and we can also include hybrid combinations of these models even in the same domain. And the workflow looks kind of like this, where we create a mesh using a tool like Qubit, for example, and take the mesh and an input file and hand it to WarpXM, which then distributes the work among GPUs or CPUs and produces a result that we visualize with Visit or ParaView, for example. Okay, so first I'll talk about the two-fluid simulations that I've done of Zpinch instabilities, and we begin with an equilibrium. We've used one called a Bennett equilibrium that just balances that J cross B pinching force with the pressure gradient force that pushes the other way. And the equilibrium ends up looking like this, where we're plotting various quantities as a function of radius divided by the pinch radius. And we see the magnetic field peaks at the pinch radius and then falls off. We assume a flat temperature profile usually. Density peaks at the middle and then falls off. And we can include sheared flows in this equilibrium. Maybe they vary linearly with R or parabolically with R like this. We typically only model a very small axial chunk of the Z-pinch, as you'll see in the next slides that show the results. Here I'm gonna be showing results from a fuse-like equilibrium with 300 kiloamps. The pinch radius is about 1 millimeter, and we have about a 33 Tesla peak field. Okay, so the two-fluid modeling shows that these sheared flows do stabilize the M equals 0 instability in the sense that I'll talk about. With no sheared flow, here are the results in this sequence. And you see at the beginning that we have the Z pinch in the middle there. The Z direction is left to right, and the radial direction is outward. these are really two-dimensional simulations that only capture this upper half plane. It's just axisymmetric. So I've just reflected it for visualization purposes. With no sheared flow, we see the instability begin to develop early in time, and then later it grows to a large level and disrupts the plasma. But if we include sheared flow at the level observed experimentally, which is about half of the characteristic speed of the plasma, or the Alfvén speed, at the edge of the pinch, we see that a very different result where the instability takes quite a lot longer to set in, and when it does, it's sheared apart, just like we saw in those schematics earlier. And the confinement properties of this Zpinch are preserved. Now, 3D simulations have been done that show a similar result for the m=1 or kink instability. And the simulations, again, use the two-fluid model, and I'm showing here the computational grid used, which is a tetrahedral mesh with 660,000 cells generated by Qubit. And I'll show a movie that shows the nonlinear relaxation process happening in 3D. This is a relatively modest simulation, in the context of this meeting, where I've used 500 cores for 2 days on Nurse Corey. But again, this is just a very small chunk of the Zpinch, and we're hoping to model the whole thing. And so what's shown here, here are isosurfaces of density in this Zpinch, and the z directions shown by the green arrow there. And what you'll see is the kink instability begin and then sort of bounce around and eventually sort of symmetrize like this, so it's circular again. This is just a cutaway showing the YZ plane at x=0 of this plasma. So you see the kink instability emerge, and then it's sheared apart by those flows, and we eventually symmetrize and develop this sort of quasi-equilibrium state. And this is really cool because this gives us some insight into what may really be happening in the sheared flow Zpinch. Okay, so another cool result is from the WarpX PIC code, where we've used it to model the charged fusion products called alpha particles. And the reason to think about this is that if we can actually thermalize or absorb these particles into the plasma, then we can actually have an important improvement in the fusion power output, and this can lead to something we call ignition. Here's some results showing alpha particle trajectories modeled in a pinch with 1.5 megaamps, so getting to this reactor level of Zpinch. The pinch radius is 0.16 millimeters. The particles are launched here near z=0 in this figure. This is just the y direction perpendicular to the axis of the pinch. And they're launched randomly, some left, some right, but they all end up drifting through these somewhat complicated orbits to the right. So this is already an interesting result. The end-on view gives you a perspective on what these particles are doing in 3D. We can analyze the bulk motion. Here's 2,000 particle trajectories shown here, and we can look at how does the centroid of those particles, how does that move over time, and we can analyze how much energy deposition are we actually getting. Final result I want to show is domain hybridized modeling that applies a continuum kinetic model where needed. And what I'm focused on here is modeling the plasma sheath, which forms at material walls. It's this very thin layer where there's a strong magnetic field as the plasma encounters this physical wall. And there are strong electric fields there and distorted distribution functions, which mean that you would like to take into account kinetic effects. So that's what's done in these simulations, where the kinetic model is applied in this edge region on both sides, where at the ends here is some physical material. And a fluid model is applied in the middle, and there's an interface algorithm for passing information between these. The colored lines show the results for density, velocity, and pressure for this hybridized modeling, and there are dashed black lines that show a full kinetic solution for comparison. And they're indistinguishable here, but in the electron solutions, they do separate some, but still we capture the essential behavior of the system. And so this is demonstrates that this is a workable concept. Finally, I'll mention that we are looking at using CUDA for GPU acceleration of these kinetic models. And one thing we've started looking at so far is accelerating this process of moment taking, where we want to integrate this distribution function over velocity space. And it comes down to just a summation process where we're doing a quadrature on our grid. And we've used CUDA because it provides the fine level of control we need for the GPU offloading and allows us to use object-oriented programming. And we're looking at, we've developed, implemented reduction algorithms in CUDA for doing these calculations, like this tree-based parallel reduction concept. So finally, I want to touch on our whole device modeling plans, where we intend to use a fluid foundation to capture the global Zpinch behavior. And with an MHD plasma model, we can couple that with the MHD plasma with neutral fluids, atoms, and molecules. And we can also include sputtered impurities, fluids, and we can imagine reaching three-dimensional calculations of this whole device with this kind of approach. We can use kinetic modeling to selectively model regions that require that level of fidelity. We can also use detailed plasma material interaction modeling to provide boundary conditions for this model. We'll have sputtering due to these hot plasma particles hitting the walls. Secondary electron emission is an important phenomenon. Recycling of those hot plasma particles, when they hit the wall, they come back as neutrals and they're ionized again. The material may evolve over many pulses. This figure kind of captures the complexity of this PMI, plasma material interaction world, and this is one that we want to focus on and integrate into our whole device modeling. We also are looking into how we're going to use machine learning and data science techniques to synthesize experimental data and modeling data to maximize the insight that we can gain from the modeling and the experimental data that we're able to take. In addition, we may be able to use machine learning-derived reduced order modeling to our advantage, and we're going to be thinking about that too. Okay, so I'm going to leave you with some results from 2D whole device modeling using the Mach 2 code. And these simulations show formation of a Zpinch, heating, and neutron production. In the top panel, we have ion density. Here we have ion temperature, and here we have neutron production rate. And at just 10 microseconds into the simulation, we see the plasma being accelerated downstream. By 20, we've formed a Zpinch and are beginning to produce neutrons. And over the next tens of microseconds, we sort of sustain this Zpinch. Sheared flow prevents the m=0 instability from rearing its head in this case. And we have this line source of neutrons that persists over this time while the current is active. As the current ramps down, we eventually reduce the temperature and the neutron rate, as shown here. Okay, so in conclusion, sheared flow stabilization leads to long-lived Zpinch plasmas and thermonuclear neutrons. We have a comprehensive modeling program that we're developing to guide our progress toward reactor conditions. We have a suite of high-fidelity, computationally efficient tools that we've discussed, including WarpXM and the WarpX PIC code. We are undertaking a whole device modeling effort to harness detailed physics into this global fluid-based framework. We're actively hiring. You can see our careers page here. We're looking for people to do plasma material interaction modeling, data science, machine learning, and more. And so work continues to fulfill my grandfather's dream of energy diversity. And we'll look forward to being back maybe next year, and we'll tell you more about our progress. Thank you.
Do you have any questions?
Well, as far as I know, in the latest supercomputing conference in November last year, there were 1 or 2 Gordon Bell Prize winner for fusion simulation. I understand those were for tokamak model, right? You're different. But just wondering, because they were scaled, they were saying to exascale, the algorithms. Just wondering, does that help in any direction? Or I understand it's a different model. You have the
Right, right.
ZP and bench.
Yeah, that's a good question. Most likely those were using an algorithm that's really specialized to the tokamak. And that's where most of the funding has been in this field for the last decades, is in tokamak research. And they use a model called a gyrokinetic model that actually doesn't apply well in a Zpinch. So we can't really leverage that, unfortunately. But we're going to be putting some resources into developing models that work well for us, and maybe we'll win one of those Gordon Bell Prizes one year. I haven't been to that conference, but it would be fun to go. Thank you.
I have two questions. The first one, you had a case where you run for 48 hours, I think.
Right.
How many iterations is this? I think it's a kind of latest Boltzmann solution, something like that.
What kind of solution?
Latest Boltzmann?
No, that one's not exactly
Because you do
lattice
iteration,
Boltzmann.
right? Until you get to the final solution, correct?
Yes, yeah. It's
So how many? I mean, 48
how many
hours?
time steps?
Yeah,
It's probably near 1 million time steps.
1 million times.
I'd have to check to be sure, but they're quite small time steps that are well sub-nanosecond.
But this is a direct solver? I mean, you solve it directly, or it's by
It's an explicit solver, so we're just explicitly marching through and updating each cell depending on its neighbor's solution, yeah. But it's a lot of time steps because it is explicit. And it has to be, it has to respect those speed limits, the Courant condition.
Hi, how are you?
Eric, yeah, go ahead. Go ahead.
Okay, two questions. The first one is about your time steps. I know that you mentioned there's a lot of physical processes happening, and usually in these kind of simulations, each of these processes happens at a complete different speed. So that's one of the biggest challenges that, for example, the community in astrophysics, they have tackled with GPUs. They normally send the fastest, the time steps that take the longest, they shoot them to the GPU, and the rest they may keep them concurrently in the CPU. So the first question is, how do you handle your different time steps?
That's a good question, yeah. We certainly do have to take small time steps small enough to resolve those fastest scale physics. One thing we do is we can artificially enhance the speed of light, for example, if we don't think that those speed of light physics are having a big impact on the dynamics of interest, we can artificially raise the speed of light. But we haven't done things like subcycling, for example. But I will say that our idea of accelerating the kinetic part of the problem is aligned with what you're saying. It would speed up the calculation of those kinetic processes, which can be the limiting, the fastest physics.
Okay, thanks. And the other question is, if any of your work has also been inspired, I'm going to go back to astrophysics. There's a lot of work of jets launched by magnetic fields, and a lot of what you're showing is very, very similar, and they have there are simulations that have done in 3D with adaptive meshes, and they have sustained these kind of structures for parsecs long. And so I wonder if that has inspired your group in any way.
I think it has. I haven't personally closely studied that research, but I'm certainly aware of it, and I know that others in our group have looked closely at that. Scientifically, it is similar. It would actually be interesting to look at what kind of modeling they've done of those Zpinches, and maybe I'll go and do that. But the codes they use are probably a little different than the ones we would use. They have relativistic effects probably they need to think about, whereas we don't. But yeah, there's a connection there, for sure.
Eric, how far away do you think PIC codes are from becoming the dominant modeling tool? And also, actually, I wanted to back that up. Do you think that PIC codes will eat into the work of MHD codes, or do you think that they'll always have, like on a 5 to 10 year, 5, 10, 15 year time scale? Do you think PIC will encroach, or do you think that MHD will kind of remain a main workhorse?
Yeah, I guess in the 5-year time scale, it's It's possible. I think in the 10-year time scale, I think kinetic modeling will become maybe more feasible to do for big parts of a plasma. I would say also that my thinking is more along the lines of a continuum kinetic approach working well to capture large regions of plasma, whereas PIC is a little more challenging to imagine scaling up to 3D, 3V calculations of an entire Zpinch device. But, that's one of those impossible problems that maybe we can solve, and maybe PIC is the right way to go to do that.
Eric, thank you very much for your talk. Thank you.
My
for
pleasure.
coming
Thank
down.
you.